So to test our pick and place pipeline so far, let's first start our factory simulation in a new terminal. Then we start another terminal and source our setup files again. Let's first navigate to the hrwros_week4 scripts folder using roscd. As we learned in week 1, let's make the script executable so that we can test it. And we will do this with chmod +x. Good. Now we are almost set to test our pick and place pipeline so far. But before we can test our script, let's switch back to the editor, and we want to see what the first two robot poses are. So at the end of each call to send the goal to the execute trajectory action client, via the execute trajectory action client, let's wait for the result using the wait for result function of the execute trajectory action client, like this. This way, we can see both robot poses one after the other. And finally, before we run the script, let's adjust our terminal in such a way that we can also see the factory simulation in Gazebo. Okay, now let's run the script with rosrun hrwros_week4 simple_pick_place.py. So we see that the robot has started moving. First, it goes to R1 home pose, and then it goes to the R1 pre-grass pose as we set up in the script. Nice. Now, let's test the non-blocking execution by commenting out the wait for result call. We switch back to the editor, comment out the wait for result call, restart our Gazebo simulation such that the robot is set back to the horizontal stretched out position. And now we run the script again. Now we see that the robot directly goes to the R1 pre-grass position, although we did send both goals to the execute trajectory action server. Did the action server skip the first goal then? Do we have some errors? Let's go back to our terminal where we started the simulation and investigate the output. So here we see the log messages corresponding to the first goal request, and we see that the first goal was preempted. Oh, indeed. This is exactly what we learned in week 1 about the simple action server. We learned that the simple action server can process one goal request at a time. So in this case, we sent a second goal request to the action server while the first one was still being processed. So the first goal was preempted and the second one was processed. Okay, so that sorts things out. In general, this is not recommended to do. Although a second goal preempts an active goal, it is always useful if we as users explicitly issue a cancel request before we send a new goal to the same server. Okay, fair enough. But what about non-blocking execution with the second robot then? We have two separate move groups and we have two separate clients that can send goals. Can we see non-blocking execution with two robots being able to move at the same time? The answer is no. Because despite having two separate clients, they are still sending goals to the same action server, which is execute_trajectory. Okay, let's now proceed with the last part of the pick and place pipeline with the help of another move group API to compute straight line motions or Cartesian paths for the end effector of our robot. We can specify the desired straight line paths as a list of waypoints. These waypoints are actually poses of the robot end effector. Now, to get the current pose of the end effector of a move group, we can use the get_current_pose API like it is shown here. Due to timing synchronization issues between the point at which we query for the current pose and the state information maintained internally by MoveIt, we could end up with an incorrect pose of the robot at the first time of asking. For this course, we will work around the problem by waiting for a short duration for the internal state to get updated and call the getCurrentPose function again, and this is usually sufficient to address the time synchronization issues. Now, once we have the current pose of the end effector, we can create linear offsets in x, y, and z directions. For this purpose, we will use the geometry_messages pose message type. Note that the getCurrentPose API returns a pose stamped message, but the waypoints should only consist of a pose message. So let's quickly check what the difference is once again. We switch to a terminal, source our setup files, and like we did in week 1, we use the ROS_MSG show command to examine the contents of geometry_msgs pose stamped message type. We see that the pose stamped message type has timing and reference frame information along with the pose message type. So for our waypoints, we have to extract the pose from the pose stamped message before we can add offsets to it. Keeping this in mind, let's switch back to our editor and let's specify an offset of +10 centimeters in the x direction and -20 centimeters in the y direction and -20 centimeters in the z direction with respect to the current pose of the end effector. Notice how the pose is extracted from the pose stamped message type here on the right hand side. While on the left hand side, we are directly updating the contents of the pose message type. We are doing this manual offset now because we don't yet have a camera that can tell us what the desired pose of the end effector should be to pick up an object. So in this week, we will only create the infrastructure for the pick and place pipeline. Next week, once we have our cameras working to detect objects, we will come back and modify this section. All right, once we have all our offsets, we can add the newly created waypoint to the list. Then we also add the current pose after the new waypoint because we want to go back to the pre-grass pose after we execute the linear motions. In the next and the last video of this module, we will find out how to use these waypoints together with the last move group API to generate linear motion trajectories and complete our pick and place pipeline.